This video will show how you can calculate an effect size for both fixed and random effects models for correlations. Just like before, I set my environment to load information from a specific directory, and now I'm going to load a file that I created before that would use Metafor to calculate fixed and random effects models from correlations. So just like we have done before, the first thing that I did after I set my working directory will be to load the library Metafor, and then after that I will load the library foreign that I need in order to load my CSV file, which is the format where I have my correlations. So the next line will be to read the file where I have my correlations, which is this read.csv file correlations CSV. So I click that, and you notice that in my environment now I have a file called data.mta that has 160 observations with 3 variables. In this case we have 160 studies with different correlations. The sample size for each one of the studies will be here, NI, and RI contains the correlations that were extracted from each one of the studies. Now the next thing that we want to do is to estimate the effect size. And you might remember that for the correlations we found that the correlations were perhaps not the best approach. So now we can see the handout that I handed to you a couple of weeks ago that shows what is the preferred approach when you have continuous variables like correlations. You can see that the suggestion is that we calculate the R to C Fisher transformation, and here's the equation. So what we are doing is trying to find the natural logarithm of 1 plus the correlation divided by 1 minus the correlation. Here's how you estimate the standard error and the weighted standard error. So in Metafor we can ask that we want to calculate a Z or R to C correlation, which is this command here. So you might remember by now that if we want to calculate effect sizes, we use this command escalc, and then we enter the type of measure that we want. In this case, like I said, is the R to C transformation. We need to enter the sample size for each one of the studies and the correlation, and where we have that information. In this case, the data is called data.mta, and we are saying once more that we want to append these values to the file. So we run the file, we run the command, and then we see what the data looks like, and you'll see that compared to the way that it was before, where we only had the sample size and the correlation, this time we also have a estimate for the effect size and the variance. And these two estimates are based on the equations that I showed you before. So now, once that we were able to estimate the effect size and the variance, then we can run a fixed and a random effects model. Now, notice that I changed the name of the file just to illustrate that you can change this to anything that makes sense to you. So this time I call the output of my meta-analysis fix.meta, and that is to indicate that what I want is to this file will contain the results of my fixed effects model. After that, I use the same lines pretty much that I used before, RMA, and then the outcome variable, the variance, and then where Metafor can find those variables, and then the method is going to be a fixed effects model. So I just click on that and then click once more so we can see what happens. And here we can see that we have the estimate for my correlation. The effect size for my correlation will be 0.2105. The standard error will be 0.0064. The Z-score and the probability are the probability is is very, very low, which indicates that in this case the model is highly significant. So since this hypothesis is testing the hypothesis that the correlation is 0, what this is saying is that the correlation is not equal to 0. And we also have a confidence interval with a lower bound and the upper bound. Another way to know that this is significant is by noticing that the confidence interval do not contain 0. So just like before, we can run a forest plot, and this time we have so many studies that this is basically very difficult to read. Here in theory what we have is the study numbers. Here on this end we have the confidence intervals, but as you can see it's very difficult to read. I don't know that we can expand this even more. It didn't really make any difference. So this will be an example where you may not be able to really see much as far as what is the effect size by using the forest plot. But what we know so far is that the result is significant, and our estimate is for the correlation will be 0.2105. Now, if we want to run the a meta-analysis for a random effects model, I have here a new variable that I call random.meta. Is the same thing that we had before, except that once more I'm changing the method, as you can see here. So we can just click on run, and then another thing that is different from what I shared with you before I just enter the name of the output. Here you can see that I enter in summary, and then in parentheses I enter the name of the file that contains the results, but it will not really change anything compared to what it was doing before. Because we are using a random effects model, you'll see that now I have estimates for tau, I have estimates for I squared and for H squared. You might remember that we said that I squared is similar to the idea of a percent of variance explained. So we know that to a large extent this random effects model is explaining about 81% of the total heterogeneity. And here we have the estimate for the random effects, the standard error, the t-test or c-score, and the probability associated with that, and the confidence intervals. Once more, we know that this is significant not only because the p-value is less than 0.05, but also because the confidence interval is not including the value of 0. We could also, because we have tau and I squared, we could run a confidence interval for those values, and here we have those estimates, and with confidence intervals for the upper and lower bound. And then finally we can run a forest plot. Once more, not surprisingly, we have so many values that it's very difficult to see anything, although here you can sort of make the fact that we have the estimate for the correlation, which is way off from the line of no effect, which is this line that runs across the file, across the chart. Just like before, we can see that there are slight differences between the two estimators, and if we really wanted to see that, we can see here that the estimate for the fixed effects model was 0.2105, and the estimate for the random effects is 0.2374. The standard error is a little bit wider for the random effects, and because of that the p-value and the z-score is not as high as it is on the fixed effects model. Same thing with the confidence intervals. They are a little bit wider in this case compared to this case here. So this concludes the description of how you can run either a fixed effects or a random effects model if you happen to have correlations.